Assalamu alaikum, everyone. Very good evening to you all. Uh, Today, we'd like to host Dr. Theresa Weston at our ASHRAE Distinguished Lecture, Bangladesh Chapter 2. Today's topic is air leakage control and the building envelope system more than energy efficiency. Before proceeding further, I would like to brief you short biography of Dr. Theresa Weston. Dr. Theresa Weston is a building science expert focused on um, advancing the durability, resilience, and energy efficiency of buildings. She founded the Halt Western Consultancy at 2020 after a 35-long career at DuPont, where she achieved the rank of DuPont Laureate, the company's highest technical level. With a degree from MIT and Caltech, she is an inventor on 4 different patents, including innovations that created new construction product categories. An active leader in ASHRAE, ASTM, and ICC, Dr. Weston has received multiple service awards and is a respected author, speaker, and contributor to building codes and standards. So without further ado, let's get started with our lecture session with Dr. Theresa Weston. Dr. Weston, I guess you have to unmute yourself.
Am I unmuted now?
Yes, you are.
Okay, good. I was saying I'm happy to join you virtually. We did pre-trial the slides and the voice, but we didn't notice that it had muted me. So I'm happy to join you virtually at some point. Maybe I can meet you all in person, but for the time being, virtually is good. It's certainly more time efficient. So I'm going to talk today about air leakage control and building envelope system, more than energy efficiency, and I'll just proceed right into the slides. So this is I am part of the Distinguished Lecturer or DL program at ASHRAE. This is a slide for being in the room. So basically, since you're all muted, it doesn't matter if you silence your phones, but I do want you to do the evaluation forms and let you know that the lecturer presentations do not directly reflect the policies and positions of ASHRAE or the chapter. However, they are in line with many of the mission statements. They are my opinions, but they're in line with a lot of the items at ASHRAE. And more information on the DL program is part of it. It's been a great program for me to be a part of for the last 5 years, and I hope you enjoy this. Also wanted to give a little bit of an advertisement for joining different committees and becoming involved in leadership at ASHRAE. It's an excellent international communication, and the networking within ASHRAE is great. Being on the committees, the very high level of technical capabilities, and I do recommend you becoming as involved as your time will allow. So moving into the topic of the day, I'm going to talk about air leakage and building performance. I'm going to talk about air barriers in particular and the building envelope, or sometimes called the building enclosure or the building thermal envelope. I'm going to talk specifically about air barriers and codes and standards in the U.S. And ASHRAE 90.1. And I realize that this is focused outside of your region, but it gives you an idea of what sort of regulations people put on air barriers and codes and standards. And then I'm going to close with a case history on the implementation of building envelope, including air barriers and air leakage control into a multifamily project. The case history is actually back from when I worked at DuPont, and I do want to let you know that I work as a consultant with the Air Barrier Association of America. So that's just with transparency, I wanted to let people know that. Anyway, so what is air leakage? Air leakage is the unplanned, unpredictable, and unintentional airflow through, into, or out of a building. And for it to happen, it needs two things. It needs a driving force, so there needs to be a pressure difference across the building, and it needs to be a pathway. And in this case, we're talking about an unintended opening. The difference between air leakage and ventilation, say, is ventilation is planned. You are doing it for a purpose, and you're trying to control it. Air leakage is happening, and it may not be happening, or is most likely to be happening when you don't want it to happen. And so I'll talk first about the driving forces. There are three driving forces on buildings that are the primary sources of the air pressure difference, which can drive air leakage into a building. There's wind pressure, and the size and shape of the building do control much of what the actual pressure is on a building, and you get pressure on both inward and outward pressure differences on the building, depending on how the building is exposed to the direction of the wind. Then there is stack pressure, which is basically based on the building height and is the natural convection forces and the pressure differences from natural convection. And then mechanical pressure, which can be, again, can be a negative or a positive pressure on the interior of the building, and can control and can cause air leakage to occur either inward, infiltration, or outward, which we call exfiltration, through a building envelope. And these three pressure differences can work together to cause a pressure profile across a building envelope at different places, and they can all cause air leakage, which can be unwanted, and I'll talk about what some of the consequences of that are. But before I do that, I just want to give you an idea of what the level of pressure difference is that you get from air pressure. From wind pressure, this is actually looking at the pressure versus wind speed. You can see it's not linear, but obviously when the wind speed goes up and the pressure differential is, usually you're at a lower wind speed than what the testing is at. Commercial whole building testing is usually done at a 75 Pascal pressure difference. And I will be talking more about how you do the testing later in the talk. And residential unit testing, where you're looking at testing an individual unit within a multifamily building, is usually done at 50 Pascals. And those have been just developed traditionally. And that is where we tended to get the most repeatable practical testing. So to give you an idea that those would be, so those are higher than the pressures that we actually see day to day on a building, but they are done to characterize the leakage within buildings. If we look at stack pressure, obviously there's I'm not going to go through the details of the equation, but just to know that the taller the building and the larger the difference between the interior temperature and the exterior temperature, the more stack pressure there will be. So if you're in a high-rise building in a cold climate, I know there's been a lot of studies on stack pressure effects on, say, high-rise buildings in Canada, where they have quite cold winters. You'll see a larger effect of this stack pressure than, say, if you're in, like, at the equator in a more where the inside and outside temperature are not that much difference. And then it does matter on the height of the building. And finally, mechanical pressure. Now, mechanical pressure is caused either by mechanical systems that are not balanced, so that you're creating either a negative pressure or a positive pressure inside the building. And they can be quite extreme. It depends on the equipment and how you're running it, how well it's commissioned, how well it's working in there. This is some work that I did on a manufactured house. So these are small. It's a very small single family house building. And what we did is we looked at the pressure difference from the interior to the exterior with a number of different devices in the house, mechanical devices in the house, turned on, and all of these exhausted to the exterior. So as those exhausted to the exterior, they depressurize the house inside. So with nothing on, with nothing on, we're close to zero pressure across the building. But then when we turned on the furnace, we went up, we turned on the range hood. This is the exhaust hood above a cooktop. Then we turned on an exhaust in the bathroom. And this was a series of houses that we did this on. So we have a range. And then we turned on the clothes dryer, which had an exterior depress. So the house was depressurized, and you can get up to quite so we got up to an average of about 12 pascals, which is, if you look back on that the wind pressure versus pressure graph, that's actually quite a significant amount of pressure on a building that cause. And these are from very small household leveled depressurization devices. And so it really, if you want to make sure you're controlling air leakage, you really need to, it takes you to having to do the commissioning of your mechanical equipment and ventilation equipment within the building to understand it. So going now to the import of air leakage in a building. So air, when it leaves, it transports heat. So obviously the air has a certain temperature and it is moving, so it's transporting heat. It also will contain a certain amount of moisture and will transport moisture, and then it may also contain contaminants, and so it may move contaminants with it. And so when we look at the impact on the buildings, the heat will cause, we usually look at the air transport for heat and its impact in terms of the energy efficiency of the building or the load on the building to condition the interior, but it may also affect the comfort. We look at moisture and its movement. We primarily look at if there's moisture in the air and it hits a cold surface, it can condense and cause moisture problems in the building and reduce the durability. But obviously, moisture moving into the building can also cause some issues with comfort and with energy efficiency. And I'll have some examples to do that. And then, of course, if you moving contaminants into a building, it affects the indoor environmental quality of that building. So first, looking at air transports and the heat. This is from some work that was done several years ago at NIST, and it is some simulated energy savings from HVAC in different prototype buildings in different climate zones. And you can see that there's savings, whether it's gas or electric, because these are averaged across some building types. In all of the climate zones, greater. These are, if you improve the air tightness, you get greater service in the cold climates than in the warm climates, and that is somewhat an artifact of the way we do energy efficiency testing, but also the temperature difference tends to be less in warmer climates than it is in colder climates. The temperature difference is greater. And then it also is different based on the building prototype, and that has to do with the energy, the size and shape of the building, and the percentage effects of that air saving percentage, air savings. But the dollars, but you do have energy cost savings in all climates and in all prototypes buildings. This is getting more into the energy efficiency of an assembly. These are some assemblies. The open dots, the open circles, did not have an air barrier, and the closed circles did have an air barrier. These are wall assemblies, a number of different ones with a simulated wind load. And what you look at an assembly, we usually look at an assembly based on its R value or its insulative values, and those are measured under zero air movement. And what you find is that if you have air movement through an assembly, you can reduce its effective R value because the air moving through the assembly will bypass some of the insulation. And so you get a lower R value. This would be a higher U value when you do not have an air barrier present in that assembly. And these are some laboratory results. For moisture control, what happens with moisture control is it moves through. If it hits a cold surface, it can condense, and you can get condensation at a cold surface. And excuse me. When we look at moisture movement, we tend to look at vapor retarders and vapor diffusion effectiveness versus air leakage. And if you look at a comparison, a calculation based on a very small hole, which would cause air leakage versus vapor diffusion, you can see that air leakage moves a lot more moisture than vapor diffusion. And so although we spend a lot of time in codes trying to control things through vapor barriers and reducing vapor diffusion, if you don't consider the air leakage along with that, you are hurting yourself because you will miss, because the air leakage just bypasses the diffusion barrier. So you need to consider the air leakage as well as the vapor diffusion when you are looking at moisture transported through the through a building assembly. And when you have a potential air conditioning on the inside and hot, humid weather, you can move it through. It can hit a cold surface, and then it condenses, and then it can cause, once it condenses, it can cause things from rot in wood surfaces, mold. It can cause corrosion in metal surfaces, a number of other harms, and hurt the durability of the building. Also, if that moisture were to go into your insulation and condense in the insulation, you reduce the insulation value because wet insulation does not work as well as dry insulation. So you can basically reduce it. Having more insulation when it's wet doesn't help you versus a good dry insulation. So you want to avoid moisture condensing within an insulation area as well, because that'll hurt the energy efficiency of that building. Finally, if we look at contaminants, one of the areas where we've looked at it in North America is at the garage house interface. A lot of houses we have an attached garage. There's a couple of little sketches of different garages attached over there. And so some work that was done up in Canada says that if more than 25% of the house air leakage occurs through the garage, it can cause significant house indoor air quality problems. And so the issue that we have with house garage is that quite often in this construction, the air leakage or the thermal boundary is different from what the water resistance boundary is, the waterproofing boundary on the building, particularly if you have an attached garage. And so sometimes people use the blue line as both the water resistance and they consider it the air leakage boundary, but really you need to have this air leakage boundary on the garage. And so this would be the same if you had a residential building over a commercial space. You might want to, depending on what was in that commercial space, you may want to separate and stop the air movement from that commercial space into the residence, and keep the air quality separate between the two. We're also seeing a number with resilience issues. We're seeing a more air quality, outdoor air quality issues. Of course, I grew up in Los Angeles, and which sort of the smog capital of the world, I think. So I've always known sometimes the air outside can be bad, but when you have a wildfire, and this is a picture of Melbourne, Australia, during the wildfires they had several years ago in Australia, but the air can be very bad, particularly with PM 2.5 particulates, and so when you look at recommendations, particularly when there is a event out there, you want to make sure that you can seal the building envelope. And if you have unknown or unintentional air leakage in the building, it's hard to seal it. If you have air leakage that's on part of a wall that you can't seal, that isn't an obvious opening, it's difficult to reduce that. This other picture is a picture, one of the things that we've been seeing in the Southwest in the US is a dust storm called a haboob. And we had one very recently in Phoenix, Arizona. I believe you probably have those in your region too. Probably you have wildfire in your region as well. And then obviously there can be air quality issues just from being near industrial sites and things like that. But these natural disasters, which wildfires and these dust storms are increasing, we need to consider how we can close off a building during these events and reduce them. And you need to have control of it. So what we talk about is basically controlling the indoor phenomena from the outdoor phenomena. And what you want to do is have the right ventilation, the right mechanical systems set up with filtration so that you can control your interior environment from the exterior. And you want to make sure that you're not bypassing all of those systems by having this unintentional air leakage. And so we talk about this building thermal envelope, and air leakage is a key part, it's a critical part of establishing that thermal envelope or enclosure. It's analogous to the largest body organ in the human body, which is the integumentary system. I always have trouble saying that word, which is basically all of the skin. And that's like 20%, 15 to 20% of your total body mass is actually doing this to you. Really, well, the analogous is the building envelope is providing that same benefit to buildings that this system provides to the human body. And so how do we do this? And this is just a basic schematic of how of the order in which you develop a system. You have your basic building design. Obviously, you need that when you're doing the building design, and then do your enclosure design, because that'll establish the loads on the building. And then after you have those designed, then you can design the mechanical, electrical, and plumbing systems that go into them and any on-site renewable energy. And that allows you to meet the loads as cleanly and efficiently as possible, but the enclosure actually helps establish what the loads are. So you can reduce the total loads and still meet them as efficiently and cleanly as possible, and that really gets you to a high-performing building. When you are establishing these enclosure systems, I do want to say that there's a lot of balancing that goes on, because these the building envelope does provide have a lot of characteristics and performance requirements that it has to meet. So energy efficiency we talk about, but it also has to be constructible. It needs to be able to be done on site effectively. We do need to handle water management, both in the liquid form from rain and vapor diffusion. It has to protect and be part of the structural systems of the building. Fire resistance is an issue, particularly in the U.S., where we use a lot of wood to make at least low-rise structures. And obviously, when you're building, cost is always an issue. And so you may get two systems that have equal energy efficiency, but they may be different in some of these other aspects. So you need to look holistically at your design, but air leakage is always a part of that design. And so we want to look a little bit closer at where air leakage occurs. It can occur through materials, or it can occur at the joints between materials. And so you can see it with the infrared around the windows, the jointing. You can see it leaking in there. And sometimes when we specify a sheet material, we don't realize that the seams in the sheet can let air leakage go through. It is harder to see the air leakage going through materials themselves, but things like insulation, like a fiberglass or rock wool insulation, air leakage will go through there. They're porous materials, so you will get air transfer through there if they are not built adjacent to an air barrier. So how do we test materials, buildings, and systems? These are the air leakage tests that we use, and these are the ones that are prescribed specifically within the U.S. codes. There are equivalent codes all across the world. They may not be ASTM standards, but they are basically based on the same physical capabilities. This is a materials test where a square meter of material is laid, a pressure differential is put across them, and the amount of flow across at a given pressure differential is measured. For an assembly, whether it be a wall or a roof assembly, is done pretty much the same as the material, except we actually build it to scale. This is a large window. It is put onto the system wall. We measure pressure across. We pressurize it, and you measure the flow across it. This rack you see in front of it, this black rack you see in front of it, is actually water. So we actually do this type of testing. We also do water testing equivalent. It's not part of the air leakage test, but is often done because many air barrier materials and assemblies are also tested for durability in terms of moisture intrusion. And then in buildings, we do what's called a blower door test, where we use an entry door of a building, and we put a fan to either pressurize or depressurize the building, and you measure the airflow that is required to keep a certain pressure differential in that between the building and the exterior. For a small home, you usually have one fan to do that. For a large building, you have multiple fans to do that, and it becomes more complicated with equipment. There are other ways of doing them. These are the actual tests that we have referenced within North American, within the U.S. codes. Then those tests all measure just how much air leakage. If you actually want to find the air leaks, we have several practices that find the air leaks. They are in this ASTM procedure, but they are there are multiple, again, there are equivalent tests with standards in other standards organizations. The two most common we use are smoke, whether it's a theatrical smoke where you do a whole building or a section of a building, or a smoke pencil where you actually can see this, where you this combined with building depressurization or pressurization, and then you can see the smoke coming out of where the holes are. The other way to do it is infrared thermography, where you're actually looking at a temperature difference, but that temperature difference will show where air leakage is occurring, and you can see the same building, the two different methods of seeing the air leakage, visualizing the air leakage in the building. There are other visualization techniques being developed. This is a continuing field of research, and I look forward to seeing other techniques that may be easier and more cost-effective to be able to find specific leaks in buildings and cure them. These are some more infrared, and this is what they call a smoke pencil. So you do this in very small area looking for it, and these are showing some of the most common places where you see air leakage in a building. If you want to find out more about these, there are e-learning available through ASTM on a number of the test methods mentioned. I think there's a cost available included in it, so I'm not trying to do a commercial for it, but there are also some YouTube videos and available to see how these programs actually work. So I'm going to quickly go through where we have air leakage and codes and standards. And air leakage is not uniformly considered in all codes and standards, although it has effects on the durability and the energy efficiency and the indoor air quality. It is not included uniformly across codes and standards. So when you look at energy efficiency, air leakage is included in the Energy Conservation Code, IECC, and ASHRAE 90.1, as well as in ASHRAE 90.2 and ASHRAE 189.1, which is the technical content for the International Green Construction Code. And this is where air barriers and air leakage requirements are the most evident. These are the ones, and so we put a lot of time and energy, personal energy, into the development of the 90.1 and the IECC requirements, because that is where it is most regulated, and this is within the U.S. codes. In Canada, air leakage was actually regulated for moisture before it was regulated for energy efficiency. So this is somewhat of a country-specific requirement. In moisture, within the ASHRAE codes, we do consider it as part of the moisture durability that their requirements are within ASHRAE 189.1. We actually have one requirement, but it affects energy efficiency and moisture durability, and it also affects indoor air quality. And then there are some areas about air leakage considered within ASHRAE 62.1 and 62.2, both minimums and maximums within those for good air quality. So when I look at and again, this is primarily US focused, but when I look at the US building energy code development, we really go through different processes. We do a model code development that then is adopted locally, and then of course it needs to be implemented in the field. So when we look at our code development, ASHRAE 90.1 is the commercial code, that is the federal minimum code. And you can see with every 3 years, a new version of 90.1 is established, and it plateaus, and then you have a decrease and plateaus and there's a decrease. But we have been steadily we've been steadily reducing the net energy use or increasing the energy efficiency of 90.1. IECC is the federal minimum in the US for residential, and it has also been steadily improving its efficiency, maybe not quite as fast as 90.1 has been. There's also a commercial part of IECC, but the federal minimum is just for the residential, and the federal minimum for commercial buildings is 90.1. So you can see from year to year, addition to addition, you get a different level of efficiency. And this is where code adoption comes in. This is our residential code adoption. And you can see that within the US, different states adopt at different rates, and the same is true for commercial. So we do have wide-ranging regional differences in what our requirements are based on state, because of what they've adopted or adopted with amendments within the US. But all of them, when they get to the field, need to be implemented. We actually need to implement in the field. And so how do we do that? What do we do? How do we implement the air leakage code compliance, which is, of course, part of the building envelope code compliance? We have maximum air leakage allowable with a whole building air test. That's one way that we look at compliance. That has been a fairly recent introduction into the codes. We do verification of tested and plus tested materials and assemblies, and then verification to make they're installed correctly. Whole building air testing, and then with the advent in the most recent codes of adding energy credits. So you have to meet a baseline prescriptive and then get a certain number of, you get to pick from a table of the number of credits that you want. Getting air leakage into those energy credits, that actually aids you in doing the testing by whole building testing and looking at the air tightness level and trying to improve them. So what are the code requirements? I'm going to go through this fairly quickly because these are the US code requirements. As I said, commercial 90.1, ASHRAE 90.1 is a federal minimum, but we also have an international energy conservation code commercial section, which follows 90.1. So they are in pairs. They're not exactly the same, but they're in pairs. And a lot of states will adopt the International Energy Conservation Code, and as long as it is at least equivalent to the current version of 90.1, it will meet our federal requirements. Residential, it's the residential part of the Energy Conservation Code, and by residential in this case, I mean single-family dwellings and duplexes, 3 stories. So these are small. So any large residential, any multi-family apartment buildings, condominium buildings, etc., would be under the commercial code area of it. And depending on your building profile within a country, most of your residential might actually end up being in the commercial code. So I'm going to just go through. As I said, they're paired. So the ASHRAE 2016 is included as part of the IECC 2018. 2 years later. So these are just a series of charts showing how this has advanced over the last 10 years. And I'll just highlight a few of these things. Back in 2016, so basically 10 years ago, give or take, whole building testing was not required. We did have a maximum leakage for whole building, but it was not required. It was an option. You could do it by whole buildings, or you could make sure your materials and assemblies met a particular level of air leakage, had a maximum air leakage level, and that they were installed, that you had you verified the design and installation of those assemblies. So you could either do it by measuring pieces, or you could measure the whole building compliance level. When we moved to the next year in ASHRAE 2018, We did have whole building testing was required. Again, it wasn't required. It was really an option, and you could test buildings in parts, or you could test with verification and materials. And but the verification design was more. There were increased requirements over that. IECC, which had the equivalent to 2019, also actually did require whole building testing under certain climate zones and certain occupancies, and then allowed for testing of individual residential units in multifamily buildings. It was a fairly complicated rubric on how you got to that. This is actually the building testing requirements, and you can see some of them depending on size, building climate zone, and the occupancy of the building, on when you had to do whole building testing, or when you could do verification and assembly testing. This is actually not quite as complicated as it looks for a given jurisdiction, because in a given jurisdiction, you're only in one of the climate zones. For a given state, you're only at the most maybe have 2 climate zones, 2 or 3 climate zones. So it does compress down as you look at it more locally, but we have a wide range of climate zones across the United States, and so it does. You do have some issues. So it was fairly complicated when you had to look at the whole United States. The most recent 2022, although ASHRAE 90.1 will be releasing 2025 this year, did require whole building testing on buildings less than 10,000 square feet. The IECC 2024 parallel code again allowed multifamily buildings to test by dwelling unit, but it also it had a different had whole building testing requirements, except for, again, it was a much more simplified climate zone square footage requirement, but they still had that. And then 2024 also had energy credits for air leakage. ASHRAE 90.1 for enhanced air leakage, enhanced air tightness. ASHRAE 90.1 2022 does not, but I sit on 90.1, and as I look into the future and the latest, we will have some energy credits for enhanced air tightness in the 2025 standard, I believe. It's not final yet, but I believe they are going to be in. If we look at the maximum allowable air leakage in those whole building tests, you can see it's been 0.4 at 75 pascals CFM and this is per square foot of the building enclosure, not of the square footage of the building. That's of the building enclosure. Of the whole building, 90.1 does not allow dwelling unit testing. As a comparison, it did tighten up in 2022 to 0.35. IECC, same for whole buildings, but they allow dwelling unit testing. And then 189.1 is a high performance building, and they have a requirement that's tighter on air leakage, whole building testing. Passive house standards, and this is and there is a proposal. It's to be published ASHRAE 227, and that's proposed, and it's proposed based on passive house standards. These are passive house standards. This is not published yet, but these are passive house standards, and they are much tighter. And you see those across, you see those being implemented as an above code voluntary, as is 189.1. And 62.2 has ventilation requirements based on compartmentalization of apartment units, basically separation of those residential units from one another, and that's somewhat tighter on the dwelling unit, and those are done on a dwelling unit basis. Notice the dwelling units are at 50 pascals and the whole buildings are at 75 pascals. Do want to do just one slide on air leakage testing. We have done tests. We did do a interlaboratory study where we had multiple testing done by different test groups of the same building, and looked at the pressurization. If you measure the air leakage when you pressurize the building versus the air leakage when you depressurize the building, and sometimes you report the mean of the two. When you pressurize the building, the air leakage seems to always be higher than when you depressurize the building, and that has to do with the types of openings that get forced open or pushed closed during the testing. And this gives you an idea of the repeatability of this whole building testing. And as far as I know, this is the first time we've actually done a repeatability of testing on a building over multiple times by different test groups. And it was an important study that went on to give us that. Finally, I want to close with a case history. This was a residential, it was several years ago, but it was a residential multifamily building. And this is from a published case history. And the modeling, they wanted to do a LEED Gold building. It was bordering on Passive House. And the model predicted an EUI of 22.9. And the air leakage model to get to that predicted was 0.16 air changes per hour, which is a little different than the numbers I've been describing in whole building testing. It's just a different way. It basically is the number of volumetric exchanges per hour that you get under a certain pressure differential, and ACH is usually done at 50 pascals. And it's just a different way of expressing the air leakage of a building. And so that was designed, it was modeled. They had the design of the building envelope. Again, we talked about reducing the load in the beginning of this talk, we talked about reducing the load on the building by reducing by building a good envelope and considering the air barrier and the interconnections in there. Then it's really important, and one of the keys to this being a successful case history was the involvement of manufacturers in the design and construction team doing mock-up wall testing to make sure the detailing was done correctly. I mentioned air leakage can occur through a material, but it can also occur in an assembly or between assemblies. And so making sure that the interface transitions and penetrations were taken care of appropriately, and mock-up wall testing is one of the best ways of doing that. And so that was done to get that correctly. And when they did the post-construction testing, they got to 0.22 CFM, which is significantly less than that 0.40, which was what was sort of in the codes at the point this was built. They got 0.14 air changes per hour infiltration rate on they sampled some of the units separately from the whole building air leakage. It was tested as part of an ASHRAE research project. And when they did post-occupancy evaluation, the EUI certainly actually came in less than the modeled. So it was about doing the design with an energy efficient loading, and they using the energy efficient mechanical systems, but also doing that construction test, construction verification during the construction, making sure that you had involvement on all of the understanding the design of the interfaces as well as the construction of the interfaces. So I think I've reached pretty much the end of my time with you. So just to summarize, air leakage is unplanned, unpredictable, and unintentional airflow. Air leakage can transport heat, moisture, and contaminants, and therefore affects the indoor environment and the loads on the building. And the primary codes regulating air leakage are energy codes. They're ASHRAE 189, ASHRAE 90.1 in the US, IECC, or other energy codes in other countries, obviously. And just some final thoughts. The building envelope or the building enclosure is a critical system to building performance. There are interactions between air leakage and mechanical systems performance. So air leakage sort of bypasses some of your mechanical systems. So it's really important to understand that and how mechanical systems can actually cause more like air leakage as well. Energy standards and codes are continually improving, and continuing to stay up with the most recent version is really necessary if you really want to move forward with energy standards. And verification is one of the key things in actually achieving the performance that you've designed. And so I'll open up for questions, and I hope you got something and I didn't talk too quickly through the technical details, because it is, there's a lot there.
Dr. Theresa Weston, I guess it's a good time for our question and answer. If you have any question, please raise your hand, or alternatively, you can write in the chat box and I can read it out for you. Next question will be coming from Mr. Padmore.
Thank you, Mr. Bapari, and then Theresa. Thank you so much for the wonderful presentation. I really enjoyed it. Please, my question is there any positive or advantage of air leakage into a building? Thank you.
Not of air leakage. I know that some people talk about using, say, natural ventilation, so air moving into the building, but you need to understand and control it. So the fact that we're calling it air leakage, that's the unwanted part. So air movement into a building through some natural ventilation, if it's planned and controlled, yes, you can be part of your ventilation system. But air leakage is the uncontrolled part of that, the stuff that you don't know and you have no control over. And that is probably not going to help you. You can move some moisture. You can dry out wet building materials if you have a leaky building, but you get a lot of negatives with that. So I would say it's not although you may get a few benefits along the way, it is not your best course of action in terms of achieving it. You need to understand where that air movement is occurring. So air movement can be a positive, air leakage, not so much.
I'm grateful.
Hope that
Thank you.
helped.
Sure, I'm grateful.
Thank you. Our next question will be coming from Mr. Moinuddin.
Hello, Ms. Theresa. Just wanted to know, in USA for energy efficiency, which code is being followed, like Title 24 or ASHRAE, what you said, ASHRAE 90 Part 1? And
so it depends where you live, because different states adopt different codes. Virtually, and then there are some states that called home rule states where individual jurisdictions adopt different codes, but so it's complicated. But so most of the states adopt IECC, and 90.1 is included within that. There are some states that adopt 90.1 directly, and then what year they adopt, there's usually a 3 to 5 year lag from. So right now we are just looking at states starting to look at the 2024 IECC. And it won't become law in those states until like 2026, and so that's early. But we've got some states that are back on like 2018 or 2012, and so 90.1 is the minimum that's required by federal. It's the federal minimum, but that codes by individual states can adopt different versions of it, and then they can adopt IECC because it has 90.1 as a pathway within it. So the answer is both IECC and 90.1 in the US. And in Canada, they mainly do their own national energy code. So
thanks. Maybe I've got my answer. And one more question. If we use SPF, I mean, spray foam in wall, floor, or roof, is this effect on air quality? Air tightness?
Yeah. So there are two categories of spray foam. There's
open cell and closed cell.
There's open cell and closed cell, right? Closed cell is a very tight air barrier when installed correctly and don't have any leakage around it. So when you put spray foam on, making sure that it's installed correctly is really important. But closed cell is an extremely good air barrier. Open cell is also reduces air leakage, but it's not an absolute air barrier. It can be an air barrier as well. It's at that level, but it is vapor permeable. So they have different vapor permeabilities. But yes, they are both good air barriers. Closed cell being somewhat tighter, but they do have to be installed correctly. The material is only as good as its installation. Yeah.
Thank you.
Thank you very much. Before proceeding to our next question, I would like to request you all to fill up the DL evaluation form. The link is shared in the message chat box at the Zoom. So our next question will be coming from Mr. ASHRAE Jaman Bhai.
Okay. Thank you for the nice presentation, and really it is useful for us. Actually, I want to know if we maintain the positive pressure, in that case, may you think any possible of air leakage for the concern in that case?
So if you maintain positive pressure?
Right.
Okay, so if you're paying positive pressure, you won't, in the building, you will decrease the amount of air leakage coming into the building, but you will actually cause some air leakage to go from the inside to the outside of the building if you don't control the air, the holes there. So I have seen design concepts where they've used pressure to try to reduce moisture-laden air coming into a building and causing condensation. I am not personally, I suppose it could be done. I think it's very hard to control and make sure it's continuing. And if you're going to do something like that, you need to make sure that you know where the holes are so that you are making sure I think it's difficult to do. Conceptually, it works in terms of moisture, not reducing the moisture coming in on air, but you still are potentially having air leakage going to the outside, and it could be an energy cost in terms of maintaining that pressure. And I haven't seen it in the field work particularly well. I haven't seen every project where they've done that. So there may be some examples where it has worked, but I'm very skeptical that you could do that on a regular basis and maintain the pressure correctly. And again, I'm not sure that it helps you with your energy efficiency. I think it just helps you with moisture, which is important. I spent a lot of my life doing moisture work. So.
Got it. Thank you.
Thank you. Our next question will be coming from Mr. Ibsa. I hope I'm pronouncing it right. Hello, Mr. Ibsa. Could you please unmute yourself and place your question? Okay, in that case, we can move to our next question. If you have any question, please raise your hand.
Can I ask again?
Yeah, sure.
Actually, in the first few slide after for the heat air transmission, 2 slide I saw, but still little confused. But those are really important. I think so. First,
When I get there, you let me know.
okay.
While I'm doing this, I will say that I have heard of certain rooms, like clean rooms, keeping a positive pressure so that you have parts of a building, a laboratory space or something, keeping a positive pressure, or doing a pressure differential to keep making sure that nothing comes into the building with a special use room. So I think that people have done. It's sort of a caveat to my previous answer.
Yes. This one, just after this, actually chart.
This one.
This one here, you informed the for the hot cloud region, actually hot region or cold region. Actually, here
yes.
we saw retail, office, and multi-family, but not.
Okay, so so that's my fault and my apologies. The cities are regions, and when you give this in the U.S., everybody knows where they are. Miami is very hot and humid. It's down at the tip of Florida, south. So this is very hot and humid. Phoenix is hot, dry. That's desert. St. Louis is in the middle of the country, and it has hot, humid summers and fairly cold, wet winters. It's actually not particularly pleasant combination. Minneapolis is quite cold in the winter, very cold in the winter, has short, hot, humid summers, but is generally cold climate. And Bismarck, North Dakota is the coldest climate, actually. It's very cold. It's a little bit drier. Minneapolis is a little wetter winter than that. So the climate zones were based on the cities, and you needed to know where those cities were. And my apologies for not putting climate zones like underneath them on the slide.
So for the hot region, their savings is less than the cold region.
That's correct. And when you look at that, it's generally because your heat transfer, you have to look at the temperature difference across it. And so the cold region, if you look at, say, I'm going to use F, sorry, 70 degrees F interior. If you go up to 90, which is quite hot during the day, that's a 20-degree difference. But if you do a 70-degree set point in the winter and you're down below 30, you may be at 40 or 50 degrees temperature difference. Okay, so that's one of the yes. That's a lot to do with it.
Thank you. Our next question will be coming from Mr. Padmore.
Thank you, sir. Just looking at the topic, it's also about energy efficiency. In this, was energy efficiency also managed, and how did it affect it? Thank you.
Money?
Manage energy efficiency, because if the building is airtight, then you may have to do maybe mechanical ventilation for health.
So with any system, you're going to need to do the balance of this. So energy efficiency, obviously, it's costs to be able to if you improve your energy efficiency, you have less operating costs, but your as-built might be more expensive because you're putting in more materials and you're doing your cost of construction may be higher. So you sort of have to do you can do a simple payback or a life cycle cost analysis on the building. Yes, air leakage. Air leakage. It can affect you, requiring you to design your systems, your mechanical systems differently. But it also can aid in being able to have more assurance of what your load is actually going to be, to know what your air leakage is so you can design to it. I don't consider air leakage equivalent to ventilation because you can't depend on it, and you also cannot filter it if you want to clean the air, because it's not coming in through a regulated space. So even natural air infiltration, you can do some filtering, you know where it's coming from. Mechanical ventilation, you can design it, as opposed to just depending on happenstance on what is happening on a particular day in terms of the amount of ventilation. So yes, there's a cost in the equipment, and there are different strategies that cost different amounts, but you can put it all into the overall energy efficiency and of the building. And so the modeling that we do with energy efficiency costs takes some of that into consideration. And then when we do a change to the energy code, we always have to do a cost effectiveness calculation and submission to show that it's effective. It's going to be cost effective to put into the energy code. And so 90.1 has a scalar calculation to make sure that we are meeting that energy efficiency. So that is sort of embedded in the code process as well.
All right, thank you.
Any questions from your side? Please raise your hand if you are having any question. So basically, I'm going to read out from the message. I'd like to copy a presentation. Okay. A question will be from Mr. Moinuddin again.
One more question regarding the sliding doors, awning windows, or some other glazing. What is the minimum air leakage value should be considered?
Oh, on a sliding door. I don't know if I have that in here. There are requirements. So sliding doors, as with any other fenestration, are tested under these models, and these test methods. The DASMA is a door method. AMA WDMA is like a sliding door, glass door test method, and there are specific requirements in different codes for those assemblies, and I would need to bring them up, but there's actually a table, very direct table where you can look at that within the codes, and I can get back to you on that if you want to send me an email to ask what that is. I can get back to you. I don't have it in my slides, and I don't have it memorized.
Okay, I'll send an email maybe tomorrow.
Yeah.
So
although I am speaking to you next week, so maybe I can pull that up and
we are going
bring
to
that
have
up. Just
a few more sessions with Dr. Theresa Weston, which is coming on 24th of September, and the other one
15th.
15th of the
next Monday.
So next Monday. On the 15th of September, we are going to have session on ASHRAE in the House, Past, Present, Future Initiatives in Residential Building Performance. And on the 24th of September, you're going to have ASHRAE Standard 90.2 2024, Leadership in Energy Greenhouse Gas Emission Performance. So I'd like to further invite you to that particular session also. Okay, if there is no more question, we'd like to get a vote of thanks from Ishtat Jaman Bhai, if you do the honor of providing a vote of thanks to Dr. Theresa Weston.
Okay. As I am from Bangladesh, as a president-elect, so I really I'm happy to get your presentation. Oh, also I want to inform to everyone, lecturer name you may found as a Weston. In evaluation sheet, you can get as a Weston, not full name. So thank you for your good presentation, and we are waiting for your next presentation. Thank you.
Thank you very much.
You're very welcome. And thank you for your hospitality, your virtual hospitality.
So the evaluation form is in the chat box. I'm going to share it with you as well as in the WhatsApp. Please do fill up the evaluation form. And our next DL session will be on 12th of September. That would be on building information modeling for mechanical discipline. That would be, we are going to host Mr. Dennis Knight on coming Friday. Thank you very much. Have a good time.
Okay. Thank you.
Thank you. Bye.